Physics, Magnetism and Matter, Part 1. Magnets. The word magnet is derived from the Greek term magnetes lithos, meaning the Magnesian stone. This refers to Magnesia, a region in ancient Greece. Magnets have a dipolar nature. Every magnet has two poles, a north, N, and a south, S. Magnetic fields are represented by lines that form continuous, closed loops called field lines. Outside a magnet, they travel from north to south; inside, they travel from south to north. The universal presence of magnetic fields. The Earth itself acts like a massive bar magnet. All matter have magnetic properties to some degree. So matter can be categorized into diamagnetic, paramagnetic or ferromagnetic depending on how its atoms respond to an external field. The magnetic field lines of bar magnet and a current-carrying solenoid are similar. Both produce dipole-like fields with north and south poles, and the field lines form closed loops exiting one pole and entering the other. So bar magnet can be considered equivalent to solenoid. Some formulas in magnetic field of a solenoid. Magnetic field. A magnetic field is the region around a magnet or a current-carrying conductor where magnetic force can be experienced. It is denoted by the letter B. Magnetic field at a point is the force experienced per unit north pole placed at that point. The formula is μ0I by 2 pi r, where μ0 is permeability of free space. I is the current. Magnetic field of a solenoid is μ0Ni, where N is the number of turns of coil. The formula for the magnetic field on the axis of a finite solenoid is also given. dB. dB is the infinitesimally small magnetic field produced by a small current element, or a single small circular loop, of the solenoid. The formula is given. The formula for the total magnetic field due to entire solenoid is also given. Magnetic field of a solenoid. We know the formula. Magnetic field equals permeability into turn density into current. So let's do a problem. A long solenoid has 500 turns per meter and carries a current of 2 ampere. Find the magnetic field inside the solenoid. The answer is calculated to 1.26 into 10 raised to minus 3 Tesla. Let's check out the elemental magnetic field due to a small slice of the solenoid. Let's understand the diagram of solenoid given. Solenoid length equals 2L. Radius of solenoid equals R. Turns per unit length equals N. Current equals IRA. Thin slice of thickness equals dx. At distance x from the center O, point P lies on the axis. At distance A from the center O, distance from the elemental slice to point P is a minus x. First we treat the elemental slice as a circular coil. Then for one circular loop, magnetic field at a point on its axis at distance c is found where z is a minus x. Then the elemental magnetic field due to a small slice of the solenoid is derived. Mathematical analogy between electric dipoles and magnetic dipoles. An electric dipole consists of two equal and opposite charges, plus q and minus q, separated by a small distance. A magnetic dipole, like a bar magnet, has two equal and opposite poles, north and south. If you look at the equations of electric dipole and magnetic dipole, they look similar. For example, torque of electric dipole equals electric dipole moment P into electric field E. Torque of magnetic dipole equals magnetic dipole moment M into magnetic field B. Gauss's law for magnetism, also known as Gauss's law for magnetic fields, is one of Maxwell's equations. It states that the net magnetic flux through any closed surface is always zero. So the equation is the surface integral of the magnetic field over a closed surface equals zero. Mathematically, this can also be expressed in differential form. The divergence of the magnetic field B is zero. It means magnetic field lines have no beginning or end.
Video by Anand Mohandas.